So, now, I want to go back. You remember this formula here?
Yeah.
And do you see how what we just did was we did that, but we did give or take this, right? So to get to the two heights that specifically bounded the middle 90%, I had to go up and down so many. So it's still the same formula, I just used it twice, going up and going down. Is that cool? When we did 69 plus or minus 1.645, 2.8, that's the formula we used, which is a formula we knew already. What did I then tweak that to be? We used that one when I took a sample of 40 dudes, right? Now, here's the real thing for Chapter 8. What Chapter 8 is it's our first step into true inferential statistics. When I take information from a sample and I try to say something about a whole population. Do we normally know this? I'm curious about this. I don't know anything. I don't know shit, so I normally don't know this. Now, to be honest, very often we don't know this either, but sometimes we actually do, believe it or not. Okay, maybe. Go with me. Okay. So when I don't know mu, what's the next best thing to use? If I don't know mu, what's mu? Yeah, X bar is the next best thing, because what's X bar? It's the sample mean. That's going to be the best guess for what mu is when I don't know mu at all. I don't know mu. Okay. So here's what this is. This is called a confidence interval. Here's the idea. And this kind of makes sense. How confident are we? Now let me ask, what was that number we got for the 40 men? It was 68.272 and 69.728. Okay. How confident are we that a group of 40 men would be in between these two average heights? This is a weird question, but look back. What did we base it on? I am 90% confident that any group of 40 men would be in between there. Why does that make sense? Because 90% of all groups are in there. So that's why it makes sense. We call this a confidence interval. Here's the big difference. Stay with me. That's all we do, Jeff, is try to stay with me. So there's a population I'm curious about. Let's say there's a population of dolphins. In fact, let me just go with this whole idea with dolphins. Not Miami dolphins, but the ones in the world. There's a population of dolphins around the world, and I know that their standard deviation of their length is, what do you got, Jeff? 1.29 feet. Right? I just went out and measured it, so you can trust me. Everybody with me? So that is something we might know from enough looking at dolphins. There's a little island with this little protected bay, and I'm looking at the dolphins in that bay. That looks like a cookie, but oh well. But aren't those dolphins in that bay still part of the whole population of dolphins? Are you guys with me? Right? Like you guys are part of the Grossmont population. You just are, even if you don't want to be. Right? There is a true average length of dolphins in this region, right? There just is. So it's somewhere. I don't know what it is. And in fact, can I measure every dolphin? No. But I can take a sample of dolphins, can't I? So let's say I take a sample of 31 dolphins. Why did I pick that? Because it's bigger than 30, which means I could do shit, right? if I take a sample, I'm going to get an X bar. Is that X bar the same as the mu? Not necessarily. In fact, I put a lot of money that it wouldn't be. It should be close. Are you guys with me? It should be close if I took a really good random sample. But to be honest, what I'm doing with this is I'm investigating these dolphins in this area relative to them. All right. So that sample mean should be close to the real mean of all the dolphins in that region. Are you guys with me? So maybe it falls like right here. Now I'm pretty sure those aren't equal. Is that cool? Does that make sense? There's a chance that a sample mean could equal the population mean, but almost certainly it isn't. Okay, maybe. If I took a sample of 80 Grossmont students, got their average age, how likely is it that's equal to the actual average age of all? Not very, but it should be close maybe, but it's not going to be equal to it. Now watch this. If I do this, if I build an interval around X bar, start at the mean, my sample mean is my best guess, go up and down this many of these, and if I want to be 90% confident, by the way, I would use 1.645 here. If I want to be 95% confident, you'll learn that we'll use 1.96 here. Blah, 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 blah. There's different levels of confidence, yes.
So you want the arrows like starting from the mean in the middle or like the...
Good point. So,
Okay.
yeah.
Also it's like or that.
So here's the cool thing. If I did use 90%, so z equal to 1.645, when I built this interval, how confident am I that that interval catches the real mean? It's the exact same question as I was talking about earlier. How confident are we that there's a certain dude in here? 90%. Because we caught 90% of all dudes, right? So I don't like fish, but I like the idea of throwing out a fishing net. And if I want to be 90% confident, I go out this far. If I wanted to be more confident, what do you think has to happen? I've got to go out less far or more far?
Less.
More. If I want to be more confident that I caught a certain thing, don't I have to catch more shit in general? So here, is everybody cool with the fact that I'm 90% confident I caught a certain dude? If I want to be 95% confident that I caught a certain dude, don't I have to go further out
Yeah.
to catch more dudes in general? I like it. Okay.
Can you? I'm just like really confused.
All right.
I understood like how we got like confidence and everything like that.
Now, and do you understand why I can say I'm 90% confident? How confident am I that I caught Frank, who's over there, in here? How confident am I that I caught him in here? That he's not out here? How certain am I? 90% certain. If I wanted to be more certain that I caught a specific person or height or whatever, wouldn't I have to go further out? My interval would have to get bigger.
So you're sure he's really in there?
Yeah. Right? So if I wanted to be really certain I caught a certain kind of fish, really sure that I caught a certain kind of fish, when I throw out a larger net, catch more fish. So I'd be more sure that I caught a certain kind of fish. Now,
And then can you explain the change of the formula or the change of the?
this is what we did earlier. Right? We made this, and then I said, what if I took a sample? So we made it again, that smaller interval earlier. And then this next step is really what chapter 8 is all about. I normally don't know this. So I have to use X bar instead.
Well, if this is for like if you're...
Yes, I took a sample. The only thing I know is the sample mean. I don't know the real mean. I'm trying to get a feel for what the real mean might be. That is the goal of a confidence interval, is to give a feel for what the real mean might be.
And that's why you're expanding your confidence level, so you make sure that.
No. If I wanted to be more confident, then I could make it go out or in. Because what did 90% do for me? It told me to use 1.645, right? If you look at 95%, you would get 1.96. You'd have to go out a little bit further. Okay. Now watch. This is ours. Let's say that this is what we did. X bar us, right? That's the one. Now somebody else, here we are, here's our little boat, right? And we took a sample of dolphins and we make this. Couldn't somebody else come along? Right? Norway, no. Somebody from some other group comes out and takes their own sample. Their sample mean will probably not be the same as ours, right? In fact, I would put money that their sample mean will be different from our sample mean because they're not going to get the same dolphins. You guys understand? They're going to pick their own sample of dolphins. So let's see if you work, Blue. Good. So here's them. And then they make a confidence interval around them. Did their confidence interval catch the real mean? No. In fact, here is the real meaning behind this. Anybody could come along and make a confidence interval. If we have several groups that make a 90% confidence interval based on their own samples, 90% of their intervals will catch the real mean. That's the real meaning behind when I say I'm 90% certain that the real mean is in my interval, because 90% of any intervals would catch the real mean. Oh shit, Jeff, yes. Let's do a problem, because this is still explanation. I know. I can see some of you guys like, just do a problem. All right. So, let's start fresh. No dolphin links. Let's do something else. So here is the formula for confidence interval. By the way, it's a confidence interval for a mean knowing the population standard deviation. So those things can change. So let's say that I take a sample of n equal to 52 things, because my creativity is gone right now. 52 things, and we know sigma is 4.98. We find x bar to be 11.07. Create the 95% confidence interval for the true mean. So the mean of the population. So we know sigma. Just like with the dolphins, we already know sigma. We take a sample at 52 and we get this sample mean. Do we know the population mean? No. So we're trying to build an interval that will give me a feel for, really gives me a feel for how certain I am about what I found, but it also can be seen as giving a feel for where the real mean is. By the way, this is finally getting into explaining where the hell they come up with when they're talking about 40% are going to vote for Buttigieg, and then whatever you say. 42% are going to vote for Warren or whatever. And at the bottom of the screen, plus or minus 4 points. Plus or minus, holy shit. That's the plus or minus in the formula. So we just have to make the formula for percentages, and then we'll know exactly where the shit they're coming up with that 4%. Okay, some of you guys are like, I could have lived my whole life without knowing. It's too bad. The wrong class. Now, the only thing that they didn't just give me to plug in, what's the only thing I don't know?
Z-score.
Z-score. Everything else they just gave me. Now, they could just give me a list of data and then you put it in 1 bar stats and you calculate X bar. Ooh, right? whoop-de-doo. But z-score is the one they don't tell me directly. But I can find it. Can you draw this? By the way, why can you draw what you're about to draw? Can you draw the situation? What would it look like?
The mean is
True, but what's it look like?
look at all.
Yeah, why does it look like a normal curve?
It's greater than 30.
Greater than 30. Kick ass.
Why didn't you do the last picture
Oh, because that was. If I would have tried to draw every single one of these, they would have gotten really. Because I had several, didn't I? I had an X bar, I had a mu, I had another X bar, and they each get their own little. I mean, that would have been crazy. So I just wanted to focus on what the interval kind of looked like by itself. Yeah. Good question though. So I want to be 95% confident. So can anybody help me figure out what those z-scores are? Or maybe you remember what I said earlier. What would this be? What area is this? 2.5. So 0.025. Can you look up what that z-score would be then? I So negative 1.96. So what's that gotta be? So now we got everything. Why don't I put negative 1.96 in here? I've already got both positive and negative. All I care about is what the number is. That plus or minus is both of those. I just have to put the number in. So now I've got everything. I'm going to start at my best guess, 11.07. Go up and down this many standard deviations. I love that the formula has this built in, because the idea is I take a sample and I'm looking at the sample mean, so of course I'm always going to do this. I'm always going to change the standard deviation. So it's just a part of the formula. By the way, this part of the equation is called the error, right? The error, because that's how much we think our guess is off by. It's 11.07, give or take. So that's why you always kind of calculate that error first.
You said 11.07 wasn't here?
No, 11.07 is the mean.
Okay.
The error is going to be 1.96 times, blah, blah, blah. I haven't done that yet. Somebody got that error yet?
1.35?
Yeah, 1.35. 354. So when you subtract it and add it, somebody understand what's happening? So we have concepts. We have concepts that tie into equations, that tie into changes in equations. And then once you go through all that shit, it becomes a plug and chug problem. Confidence intervals especially are just plug and chug, but there's a ton of concepts underneath them. What's that? Everybody doing all right?
Yeah.
So I get 9.72 up to 12.42. Roughly. Yes. Say again, sorry? All right, be careful. No, the standard deviation is 4.98. Do I know what the real mean is? In this whole problem, do we know what the real mean is?
No.
Don't have a flippin' clue, right? and this is statistics for you, our results, when we don't know anything about the population, will always be uncertain. That's my one green shirt that says statistics means never having to say you're certain. You're always plus or minus this percent, or plus or minus 1.354, right? Because we don't know mu. But a sample, if I really do take good randomly selected 52 sample size, its mean should be close to the real mean. Right? Now randomly I could just happen to get one that sucks, but how often will my confidence interval not even catch the real mean? Can anybody tell me what percentage of confidence intervals would not catch the real mean for this, what we did? 5%. Because it's 95% confidence. So that means that 95%, if somebody else came along and got their own X bar, made their own confidence interval, and like 100 people did that, made their own intervals, 95 of them would catch the real mean, 5 of them wouldn't, on average. So one thing I like to do, like at the beginning of the next class, I think, we're going to have you guys analyze, I'm going to have the men analyze male final grades for the last few semesters, and the women do the female grades. You're going to make a confidence interval for both. Then I'm going to tell you what the real average is, and I normally get a decently close, like if I have 50 people, or if I have like 20 groups, stay with me now. If I have 20 groups, and they all make a 90% confident interval, what percentage of them should not have the real mean in there? 10%. 10% of 20 is 2. So always have around 2 that doesn't have the real mean, and it kind of kicks ass for me, anyway, because it shows the concept is true. That's why.
But did they get the right numbers?
So here's the problem. Here's the thing. If you create an interval, and I know the real mean, and your interval didn't catch it, that doesn't mean you did anything wrong. You didn't do shit wrong. Well, you could have, but even if you do nothing wrong, your answer could still come out wrong. You know, not catching the real mean in this case. Why is that fine? Because it's built on the possibility that it doesn't come out right. I mean, this is where people kind of give up on stats, but this is why stats is the best freaking math, because it's the most honest. It's like, this is the best I could do because that's what life is like, God damn it. So a math can't come along and tell you exactly which lottery ticket to buy. I'm sorry. You got all kinds of stupid people making websites and making people pay for information, which is all bullshit. Because math can never do that for you ever. The best it could do is give you possibilities. That's it. That's why I love this math. And it doesn't mean it's not useful, right? Just because it can't tell you for sure what the answer is doesn't mean it isn't useful. It can tell me what thing to do based on the possibility of living or dying, right? The higher chance to live this way, I'm going to go that way. Does that mean I'm going to live for sure? No. But it was good to have that information. I have a higher chance of living if I go that way, right? Okay. So, I haven't even gotten to the best part yet. You're going to love this. You ready? Every time you construct a confidence interval, you have got to give me a conclusion. Here's how it's going to sound. In this case, we are how confident? 95% confident that the interval, where'd it go? 9.72 things. No, I don't know what the hell I was going to measure. I didn't make some out. Normally I want units here, but I didn't give units. You with me? So 9.72 units to 12.42 units. So this could be pounds of candy, or it could be centimeters of lumber, or whatever. You've got to put in units there, or else I'm going to be a dork and take points up. We are 95% confident that the interval we made, that to that, contains the true mean of the population. So there's only a 5% chance that our interval doesn't catch it, that our interval doesn't represent it. That's pretty good odds. It's much better than normal for me. Only 5% chance I'm wrong. It's pretty good. So I'm gonna do this. I'm gonna give you guys this. We're gonna do it on Monday, but I'm gonna go ahead and give it to you. Number 1 is exactly what we just did. Number 2 is gonna be section 8.3, and then the back is gonna be 8.2. The reason I do 8.2 last is because we're gonna use a different distribution. We're not gonna use z-scores. We're gonna use something else. You're gonna get a whole other chart. Yeah, and there's gonna be another chart after that. And that'll be enough charts, right? So don't forget to bring this back Monday. You can try the first one out if you want to.
So we're up to
8-1, yeah. So on Monday we'll finish up 8, and then we'll devote the rest of the time to review.